Hey guys, so we're going to do questions 10 to 20 in the Software Design and Development Exam 2018. So let's get into it. So question 10 is, a programmer can make use of stubs to A. Reuse previously written and tested modules. B. Help clarify the operation of the software to the user. C. Improve the performance of the code by removing unnecessary detail. Or D. Test the logic of the main line without having to fully code all the modules. Now, the answer to this is simply D, because that is literally the definition of a stub. And if you think about a stub, so say if you had a program in pseudocode like begin program, and then you had like a subprogram, and usually a subprogram has the line underneath. This subprogram might be required by the rest of the program, but we don't want to code it straight away because we want to test everything else first. So in the subprogram, you might just have something as simple as, display, to do, basically, and you just write a note saying to do, or you return just like just default. You just return like some zero values, basically, and so that's all like really a stub is. So to look at the other parts of the question, it's not those. So it has nothing to do with. These are all just wrong. All right, question 11. During which stages of the software development cycle is benchmarking relevant? Okay, and it lists all the stages. So if you know, there are 5 stages. So the first one is, define the problem, define. Second is plan the solution. Third is implement. 4 is testing. And 5 is modify and maintenance. So what benchmarking is basically we want to compare the performance of the actual implemented solution to what we planned the performance should be in the planning stage. So in this case, it's not C or D because we don't worry about benchmarking when we're defining. And we don't exactly worry about the benchmarks while we're implementing the solution. All we care about is actually the planning and testing and evaluating. So yeah, the answer to this question is B. Okay, moving on. Question 12. A railroad diagram is shown. Which EBNF definition is equivalent to the railroad diagram? Now, when we're doing, so this is a pretty common question, is translating an EBNF diagram to railroad and vice versa. So knowing all the symbols is pretty important. In this question, it's pretty straightforward, so let's look at it. So how to think about a railroad is you always go left to right. You start here and you follow the line as if it was a train. And then this means a loop, so it means you can repeat and you go back. And notice how the angle is quite rounded to show that it's a loop. However, at this point, this is an option. And the reason that it's an option is because if a train was trying to go along this, it couldn't go backwards, basically. It couldn't go either way because the angle is so steep. So see how it's like this? This angle is too steep for like a train to go round. So this is actually considered an option. So it's an option. And once again, we have another loop. So that's all you really need to know, a loop and an option. Now, when we look at EBNF, there's a bunch of symbols here, so let's run through them quickly. The braces, the curly braces mean 0 or more repetitions. The big line means or, and the parentheses means grouping together. Right, so in order to tackle this, I would say break it up. So look at the first part of it and say, okay, which one of these is correct? So if we look at our train, we're coming along. So it means it's an optional loop. So the curly braces means optional, which is fine. And as we go along, the first symbol we hit is the 5, and then the second one is the X. So if we look at our diagram, we can instantly eliminate B and D because X5 and X5, it's impossible because we always have to start with a 5. So instantly we can get rid of 2. Then we look at the next part, M or 5, and we can look here, it's M or 5, so that's fine. And A and C are identical. Now we look at the last part, and this is where they differ. It's 5, repeat 5, or just repeat 5. Now a lot of students will get this wrong because they think like, okay, it's just a repetition, yeah? It's just one, it's just, there's 1 5 here, and then there's a loop. So obviously the answer should be C, right? And unfortunately you'd be wrong because with a loop, it's 0 or more repetitions. 0 or more reps. But in the railroad diagram, the train has to go through the 5 at least once. So in order to translate that to EBNF, you need to include 1 5 that's guaranteed to happen. So this 5, no matter what, is guaranteed to happen, and then you have 0 or more optional 5s. So the answer to this is actually A. Moving on. Question 13. Question 13. Which row of the table correctly identifies all the search methods that can be used for sorted and unsorted arrays? Okay, so in order to understand this, so an array is simply a bunch of numbers. So this would be an example array. And a linear search, all that happens is you start at the first element of the array, you search it, and then you go to the next one, the next one, the next one, so on and so forth until you hit the end of the array. Now a binary search instead finds the middle element of the array, asks whether that element is greater than or less than, and then based off that, it will ignore one side of the array and then start searching the new middle. So I'll use an example. So if I had like 3, 5, 7, 8, 10, and let's say my target number is, I don't know, 5. So I look at the middle, I look at the 7, and I say, okay, is 5 greater than or equal to 7? It's less than. So then what we can do, because we're smart, we can eliminate this whole right side because we know that there's no way that 5 can be in it. However, the key point is this array needs to be sorted in ascending or descending order for us to do this. For the obvious reason that if I eliminate this side, I assume that everything on the right side is greater than 5. So the array needs to be sorted. Then I would go to here, and in the case of a binary search, when there's an even number of elements, you have to define what the middle is, whether it's the lower middle or the upper middle. So if you were to assume it's the lower middle, so this is the lower middle, we'd check the 3, and obviously 3 is less than 5, so then we'd eliminate that and then check this, the only middle, which is 5, and then we say we found our element in a search. So in this case, if the answer isn't obvious, a binary has to be in a sorted array. Now, most students would pick A because it's obvious, but remember, a linear search can work on any array, whether it's sorted or unsorted. So in this case, the answer is actually C. So a linear can work on a sorted array as well. Okay, moving on to question 14. Consider the flowchart fragment. Alright, so with the flowchart fragment, a common thing, once again, is learning to translate between a flowchart, an algorithmic flowchart, and pseudocode. So this is quite an involved question. So basically they say, here's this flowchart, and they ask you which pseudocode represents the flowchart. So the best way to do this, so we can zoom out a bit, the best way to do this, so they give you all these options, right? The best way, so instead of trying to do this all on your head, I recommend you do a desk check on this. So what we're going to do is we're going to write k, we're going to write k equals 9. Does k equal 9? Question mark. And then we're going to write, k times 3. And what I've basically done is grabbed a bunch of points of interest on the flowchart that we want to look at. So now I'm going to draw this table. So I'm going to say k equals 1 because we see it here. Is k to equal to 9? That's false. So that's a Boolean. That condition is a Boolean, so it equates to false. Display k times 3, so we display 3. So notice in the question it says output. So the output is defined by this rhombus, because a rhombus in a flowchart is input output. In this case it's the output because it says the word display. And obviously the triangle is a decision, which is a Boolean, which is true or false. And as you can see here, just from looking at it, what we're doing is basically we're doing a loop, right? We're looping back, and that's what the arrow is. When you see an arrow, it usually means it's a loop. If the arrow is going back up to the top of the flowchart. Okay, so we've got 3, and now we add 2 to k, so that becomes 3. So 1 plus 2 is 3. We go back to the top, we evaluate the condition again, and obviously 3 does not equal 9, so it's false. Then we output 9 because 3 times 3 is 9 from here. Add 2 to k, so that is 5. And basically, like, we just keep, we'll go through the same motion. So 5 times 3 is 15, false. Then we have 7 times 3 is 21, false. Then what's interesting is we get to 9, and we have to ask ourselves, does 9 equal 9? Well, it's true. And then we exit the loop, right? So this is the desk check for our flowchart. So now what you've got to do is go down here and basically look at pick one of these that you think is the most correct and do a desk check on it. So let's just, for example, let's say, we thought it was A. So now we have to do another desk check. I know it's annoying, but this is how you got to do it. So it's annoying, and maybe you could do it in your head, but the risk is if you don't do this and you don't do the work, you could get it wrong because it's very easy to get wrong. And this is probably like a band 6 kind of question simply because it takes so much time and it's only worth 1 mark. So yeah, you got to put in the work to get this mark. It's a really hard mark to get. So we're looking at this pseudocode fragment and we're going to do a desk check. So k equals 1, while k is less than or equal to 9, display k times 3. So that's false, so 3. Then we add 2, so it's 3, false. And we can kind of see, at this part, it's kind of obvious that it keeps incrementing. So 9, 15, 21, 5, 7. But the key point is we get to 9. And while k is less than or equal to 9 would be true because 9 is less than or equal to 9. So this would actually, this wouldn't be false. This would be true. K is less than or equal to 9. So this would all be true. and then this would be true for 9, and then because it's 9, it would output 27. And since it outputs 27, that's not what the flowchart outputted, so we have to, obviously, this is not the answer, right? So then we get rid of the board. Okay, so, you could do that. Basically what you need to do is do this for every single question. So, but if we were smart, or smarter about this, we could, maybe instead of going sequentially A, B, C, D, we could look at these again and say, okay, obviously we know that 7 has to be the terminating value to output 21. And if we go past that, it's not right. So if we look at B, for 1 to 9, so with a for loop, this is inclusive. So that means that we are actually going to output whatever 9 is. So that can't be right. So when we say for k equals 1 to 9, it means we go from 1 to 9 inclusive, including the 9. So that means that just by definition, B can't work. For C, we stop at 7, which means, so we go from 1 to 7, step 2. So that means we'd go 1, for K would go 1, 3, 5, 7, and stop at 7. So I'm liking that. And then obviously display K times 3. So since we've got 1 to 7, step 2, 1, 3, 5, 7, it's very likely that C is the answer. So you could do a desk check on D. D is very strange, but it potentially could be the answer. But as I said, you just got to do a desk check on that, and basically what you reveal is that D is also incorrect, because I think it also goes to 27. So if we did desk check on C, you'd realize that it stops at 7, and just by looking at it, based on a for loop, that it stops at 7. Okay, so moving on. 15, well, what level of testing does acceptance testing occur? The answer to this is D, system level testing. Acceptance testing is just a general kind of engineering term, and it's you just kind of need to know the fact that this happens at the system level. A lot of these are just kind of nonsense answers, right? It's just a general engineering term that acceptance testing occurs at the system. And basically what that means is that when you test something, you want to make sure that it's within an acceptable level, right? So an example would be, say you have a giant, a crane that's in construction, and you want to test the load that crane can hold. What they do is, with the crane in construction, is that they have these giant cinder blocks. And you connect the crane to the cinder block, and you know how big the cinder block is and how much weight it is, and so the crane lifts it to test that it can successfully lift this giant concrete cinder block or block of concrete, because obviously if it can't, then you don't want to be lifting valuable equipment that is actually worth millions of dollars and drop that. You'd rather drop this giant block of concrete instead in a safe, controlled way. So that's what acceptance testing is. So, all right, question 16. What is a program counter? Okay, so first off, so basically, once again, this is just knowing your definition. So not even looking at the options. A program counter is where you store the instruction. The program counter is where you store the address. The program, okay, so actually what we should do is, this question is broken into two parts. So this part and then this part, right? So what we're going to do, a better way to do this is we look at this. So it's is a program counter a register or a variable? That's the first thing we should ask. And then we can eliminate two of the options. So a variable is in software, right? Like if you're writing code, you have a variable like an integer or a float or a boolean or a string. And this a variable is like exists in software, and it's like how we're able to do perform calculations and store important data using a variable, right? Now, a program counter, this is not a software concept, it's a hardware concept. It's actually a physical hardware component, and that means that it's a register. A register is a physical component on your computer. It's not in software. It's not purely a software construct, it's a hardware construct. So in that way, we can instantly eliminate B and D. Now, the next part is a program counter a register that holds the next machine code instruction, or does it hold the address to the next machine code instruction? And this is where you just need to know the definition that a program counter holds the address of the next machine code instruction, not the address itself. Not the instruction itself, I should say. It holds the address of the next machine code instruction. So that's what you need to know. Now, to unpack all these words just for a second. So in memory, so how your computer allocates memory is it has a bunch of addresses. And usually the addresses look like this, like 0x7 something or other, right? And the idea is the program counter holds the address, and the addresses are just like, in this kind of sequential way. And when you hold an address, the address points to a memory location, and at that memory location is the instruction or the code that needs to be executed. And the program counter is part of the fetch execute cycle, which is what the CPU does to execute instructions. It's part of the So I won't go into too much depth here. There'll be other questions where I'll go into more depth there. But basically, this just comes down to you just need to know the definition. All right. Question 17. The following code fragment was developed to display the words at a competition based on scores up to 100. This question comes down to just knowing how the multi-way selection or case-where control structure works, right? So the easiest way to answer this question is ignore this, because you'll get ignore what you think the code should do. So most students, when they look at this, they think like, okay, if I was to enter, so the question is, what is displayed if I enter the score 51 into this, right? Into this question. And obviously, normally what you'd think is that, okay, if I get a 51 in my exam, that's technically a participation, right? It's not a fail, it's a participation. So you'd think like, okay, well, it'd be go there. Oh, actually, no, according to this code, right, it says less than 51. So then you ask like, okay, well, is 51 less than 51? And the answer to that is false, right? So then you think like, okay, well, then it's a credit, right? So then you think, okay, well, then it's A. However, that's like what logic, that's like kind of what, that's how you'd think about it in terms of that logic. But if you just follow the code and ignore everything else, and we go through it line by line, so we input the score here, then we go to a case where 51. So then we go to the first, so how a case where is evaluated is you start at the top and you go your way down, and as soon as you find a condition or a case where the value equates to true, then you execute that line and then you exit. So the first line is less than 91. So how you'd how the algorithm would work, or the control structure should work, is score less than 91? And since score is 51, you ask that, okay, does this Boolean condition equate to true or false? And then, well, it's true because 51 is less than 91. So it would display distinction. So the answer is actually B. So that's actually like a logic error. So technically, it should be credit. It shouldn't be a participation. But how the code executes is that it actually satisfies the first condition. So, little tricky part there. Okay, 18. The table shows the contents of an array and the contents after one pass of a valid sorting procedure. What are the contents of the array after the second pass? So this is like probably a band 6 question, once again, because it's going to take so much time to solve. Because to answer this question, you need to understand very well a bubble sort, a selection sort, and an insertion sort, and you need to know exactly how they work, like back to front. So if you see this in the exam and you it's probably best you leave this to the very end. Like, I wouldn't attempt this because it's only worth 1 mark, remember. So this is a very involved question. So basically what we're going to do is, so in order to answer stuff like this, you need to basically look at the data and apply each of these sorting algorithms to the data, and you have to apply them in a bunch of different ways. So basically, when you understand the sorting, you can start from this element and work your way right? That's the first question. Or you could start from this side, from the right, and work your way this way, right? That's the first thing you need to ask. And then the other thing is, you have to actually define how is it sorted? Are we putting the smallest element here and then putting the largest element here? Or are we going to go and put the largest element here and the smallest element here? So, because we don't know the implementation of each sorting algorithm, we basically have to, any of those possibilities could exist. So we have to basically examine every possibility to see if potentially there could be the right fit. So I'm basically going to explain that right now. So let's assume it's a bubble sort. Just assume it's a bubble sort, and let's look at it. Okay, so instantly we can kind of know it's not a bubble sort, because after one pass, some of the elements should have moved, right? Because in a bubble sort, you basically go through it and you compare all the elements, and if one is, say, less than the other, you do a swap and you swap the elements. But since none of the elements in the one pass, so the other thing is, one pass of a bubble sort is when you examine and compare every element and you hit the end of the array. That would be one pass. So by definition, since nothing has moved and something should have moved, it can't be a bubble sort. So so that's one we've eliminated. So let's go to the next one. Let's assume it's, I don't know, a selection sort, right? Now how a selection sort works is you have to do a linear search on the entire array, and then basically pick either the largest or the smallest, and then you swap it into the adjacent part. So how you think about this, and this is how you think about insertion, is that assume there's like the unsorted part of the array and the sorted part, and you basically want to grab, with selection, you want to grab the smallest or biggest, however you're doing it, element, and then stick it into the sorted part of the array. So that's selection. So if we were to take selection and apply it, okay, so let's look at it. So with this case, we need to basically go through all those possibilities I mentioned, right? That we're going to sort it left to right, we're going to sort it right to left, let's say the smallest value is going to be on the left side and the largest value, let's say left, and the largest value is going to be on the right, or the largest value is on the left and the smallest value goes on the right. So those four possibilities we need to apply to this, right? So let's assume we're going to go left to right, and let's assume that the smallest value is going to go here and the largest will go here. So if we were to assume that, let's say we search, we grab the smallest value, so it'd be 1. So in that case, we should have swapped it with the 3 to put it here. But since we didn't do that, that doesn't work. Okay, so let's go right to left. So we go right to left. So when I say right to left, I mean let's assume the sorted part of the array is going to be stuck on the right. So we go right to left. Let's assume that put the smallest here. We'll assume the smallest goes here and the largest goes here. So we'd grab the 1 and then we'd swap it over there, but since we didn't do that, that doesn't work. So let's assume left to right and the largest goes here. That doesn't work because then we'd grab the 8 and we would put it there, but we didn't do that. So then the final combination is we go right to left and we grab the largest value and stick it here. Now, this actually could work because assuming 8 is the largest value, we do a linear search, find that 8 is the largest value, and since it's already in the correct position, we wouldn't swap anything. So this would be actually a valid selection sort, one pass, if we're going right to left with the largest value going on the right side. Yep. So now then basically what we need to do is, if under that assumption, we need to do the second pass. So the second pass would be we grab the largest value, which would be 6. Oh no, sorry, not 6. We'd grab 7 and then we'd swap it with the 4. So it should be, the second pass will be this, and the 7 goes there. So it should be 3, 1, 5, 4, 6, 2, 7, 8. That would be the second pass. So then we look at our multiple choice and we say, does this exist? Okay, so it's not A, it's not B. Yeah. Okay, so this solution does not exist in the answers, so that means that it can't be selection sort. Okay. So then the last one we have to assume is that, okay, let's check insertion sort, right? So how insertion sort works is that instead of doing a linear search of the entire array to find the smallest or the largest, we basically do one comparison and then insert that value into the correct spot. So I'm not going to do the insertion sort for every combination, so I'm just going to jump to the answer that I know it is. So you'd have to do every combination, right? But so you'd have to do like left to right. So okay, so let's consider the possibility that okay, let's go through the whole thing actually. So let's assume it's left to right, and then let's assume that it's the smallest is going on the left, the smallest element's going on the left, and the largest is going on the right. Okay, so we do a comparison. So we assume, so with the insertion sort, you assume the first element is sorted, and then you do a comparison to the next one, right? So if this was true, if we're going through left to right, smallest left, largest right, then the 1 and the 3 should swap, but they didn't, so that doesn't work. It would work if we're not doing that, but we're doing the largest is going on the left, right? Because if we did 3 and 1, well, 3 is bigger than 1, so we leave it where it is. So that would be correct for one pass. But if we did a second pass, what we do is we compare the 1 and the 5, we'd swap those, and then we'd compare the 3 and the 5 and swap those, and then that would be one pass. Because we want to insert the next adjacent value into the correct spot. So the second pass would be 5, 3, 1. That would be the result. So 5, 3, 1, 7, 6, whatever. But if we look at the first element, there is no 5, so that can't work. So then we eliminate that possibility. All right, so basically what we've done is we've eliminated any possibility that we're working left to right. So it has to be right to left. So obviously we can see a big value here, so it obviously can't be, since the 8 is here, we can assume that it's not the smallest on the right. So the only thing left is the largest value is on the right, and the smallest value is on the left, and it's going to be an insertion sort, and we're not going left to right, we're going right to left. So let's do that. So we'd compare the 4 and the 8. We wouldn't swap because 8 is bigger than 4. Then the second pass would be we compare the 2 and the 4, but since 2 is less than 4, we leave it as is. So the result would be the second pass, we didn't change anything again. And if we look at the option A hasn't changed at all. So A is in fact the answer. If that sounded like a lot of work for 1 mark, you'd be right. So that's definitely a band 6 question. So all the other answers are just nonsense answers and they don't make any sense. B is basically like a bubble sort if you were to do 1 pass, but obviously we're looking at the second pass, so it's not right. Okay. So question 19. An item in an array containing n elements needs to be removed, and the elements following it shuffled back. As an example, the diagram shows the array list before and after the number 4 is removed. Which code is best able to achieve this? Okay, so once again, they give you a bunch of so this is probably another band 6 question. They give you a bunch of they give you all the pseudocode, and here's this array, and basically which pseudocode answer can solve this problem, right? Now, the best way I would suggest that you do this is, once again, do a desk check. You know, it's kind of slow and annoying, but you know, very easily you could get overwhelmed, and if you try to do this in your head or try to jump the gun, you won't do well. So how I would do this, so instead of writing index, I'm just going to write the value I, because writing out index each time is going to be annoying. So you've got I for index. So with the desk check, once again, I'm going to pick out points of interest. So index is interesting. List index, list I is interesting. And then obviously list, I plus 1 looks interesting. And that's really all it is, right? So I'm just going to jump in and let's just assume that A is correct, and let's test it. So what you also want to do is, as you're doing the desk check, you want to actually modify the array as you're going along. So you could just draw it out. So 1, 2, 3, 1, 2, 3, 4, 2, 3, 4, 5, 6. Yep. So you're going to basically fill in the array as you go along, just to know what's happening. Okay, so we're going to go through this code A, and we're going to just go line by line. So get location of element to be removed. So the location of the element. Okay, and the other thing is, one more thing, is that assume the array starts at 1. So the location of the element to be removed is number 4. So number 4. So the location of number 4 is location 3. So this is location 1, 2, 3, 4, 5, 6, right? So location 3, the value at location 3 is the number 4. So location would be the value 4. So then we say for index equals location, so index would equal 3 to n minus 1, and n is the number of elements, which is 6. So that means n would be 5. Right, so basically we're going from 3 to 5. So list index, so first off, what I want to do is just write out what's happening. So list index, what's at list index? So index would start at 3, so list index is the value 4. List index plus 1, so that would be list 4 is the value 8, as you can see. So list 4 is the value 8. Now, so what we're doing is whatever was at list I, we're going to set it to whatever's at the next one. So the 4 is going to be overwritten with 8, right? So we're going to have 3, 5, 8, 8, 7, 2. Okay, so then we do it again. So then what happens is we increment. So since there's no next to the for loop, you assume that the counter or the index is going to be incremented by 1 every pass of the loop. So if we increment the index to value 4, and then we say, okay, what's list 4? Well, list 4, so now we have to use, what you're writing here. So list 4 is the value 8, and list, I plus 1 is the value 7. So then we overwrite the 8 with the 7, so we can do that, get rid of the 8, put in the 7, and yeah, then we do that again. So then we increment I to 5. So we've hit the terminal value, but we since a for loop is inclusive, we execute. So what will happen is we will do list I. So list I would be list 5, which is 7. So it's this 7. And then list I plus 1 would be 2. So basically we overwrite the 7 with a 2. And then we end. And then it says clear list n. So list n is the value 6. So we clear the 2. Get rid of it. Okay, so we're left with 3, 5, 8, 7, 2, which happens to be the answer. So we got lucky. We chose A and we got lucky and we found the correct answer. So the answer to this question is A. Now, basically, you might not get lucky. You might have to go through all of these and basically do that sequentially. Do a desk check, write the array as it changes along the way. We can just you can look at why the others are wrong as well. Like you can see in this loop, you don't start at the location, you start at n. So index would be n, so you'd start at 6. And then basically you'd say, okay, list index, which is 2, equals -1, right? So in D, the very first thing that happens is you overwrite the 2 with a 7. And as soon as you see that, you'd realize, oh, well, you've lost the 2, so that can't be the answer, right? So that is wrong. And then the others are, so basically, if you went through all of them, you basically realize that they're all wrong. So, but that's what I would do. Like, I would just pick A, desk check it, see if it's right. If it's wrong, go to B, do the same thing. And if you want to be really quick about it, you could maybe do a quick pass over all the options and kind of maybe think, okay, what is the most likely to be the answer out of all of these, and then desk check that. But if you don't want to do that, you could literally just go sequentially A, B, C, D and desk check it until you find the right one. Cool. All right. So question 20, lucky last. A driver has been developed to test the logic of a module. Which of the following best describes the use of a driver? This is you just need to know your definitions. So a driver is the answer to this is C. So it calls the module with a range of values and displays the values returned. It doesn't mimic the logic of a module. It doesn't call repeatedly until a required output is achieved. It's simply used for testing, to like use test data to execute a module and see what's returned. That's it.